The second topic of this week is feature selection. In this lecture, we will show how to select the best features and why. We will introduce the concept of feature importances, and we will interpret these feature importances as well. And we will cover several feature selection methods, including univariate feature selection, model-based feature selection, and recursive feature elimination. So why would we want to select features? There are several good reasons to do that. Feature selection is performed to reduce overfitting because less redundant data means less opportunity to make decisions based on noise. It's also done to improve accuracy because less misleading data means better modeling accuracy. And finally, it's done to reduce training time because fewer features mean lower model complexity and faster training. So our application is prediction of ages scan from volumes of 86 brain structures of preterm babies. We have already seen this data set before. And if you recall from a regression lecture, we have seen that multivariate linear regression overfitted this data set. Of course, because there were many features, 86. And we can recognize overfitting if we calculate performance measures on whole training data sets and using cross-validation. So for example, for root mean square error, we had below 1 week on whole data set and over 2 weeks using cross-validation, which is quite a big difference. So it was overfitted. So we already covered several machine learning techniques that can prevent overfitting. So I will leave you a couple of moments now to recall which ones are they. So we have covered regularization that prevents overfitting by penalizing large weights using L1 or L2 norm. We also covered dimensionality reduction, such as principal component analysis. We covered ensemble learning that we can also use to prevent overfitting, and a good method is random forest. And this method is very resilient to overfitting. And finally, today we will describe feature selection. We will demonstrate the concepts behind feature selection methods using 5 simulated features. And these features have different levels of noise and nonlinearity. So here I plotted these features for you. On x-axis, we have plotted the feature values. On y-axis, the target values. So we want to predict the target values. And the first two features are linear, but feature 0 has lots of noise, while feature 1 has a small amount of noise, so low noise feature. Feature 2 also has low noise, but is slightly nonlinear. It is actually a polynomial feature, but it's still relatively close to linear. Feature 3 is highly nonlinear, as you can see, and it's not even unique. So for the same feature value, you can have different target values, which makes it very difficult for prediction. And finally, feature 4 is just noise, so it has no relationship to the target values. So what are feature importances? If we want to select the features, we need some measure of importance of each features, and how we could calculate this kind of importances. So one way to do that is calculate univariate feature importances, which means that we will consider each feature separately. So we will evaluate how this single feature predicts target values or labels, depending whether we work with regression or classification. And for example, we can use correlation coefficients or mutual information to do that. Another type of way to calculate feature importances is model-based feature importances. So, for example, for linear regressors and classifiers, we always fit multivariate linear model. For regressors is for prediction, for classifiers is to fit the decision function. And the coefficients W1 to Wn then measure the importance of each feature. So obviously, if this coefficient is 0, then this feature doesn't contribute to the model at all, so it's probably not important. But for these coefficients to be actually meaningful, it's very important that the features are scaled before fitting. So, for example, by applying standard scalar, then we can interpret the actual value of W as feature importance. In scikit-learn, the coefficients are stored in attribute model.coef, and we will use this attribute as a feature importance. A different type of way to calculate feature importance is in tree-based methods. So in this type of method, we can calculate how much each feature decreases the impurity in a tree. And if we have an ensemble of trees, then we can average over all trees. And in scikit-learn, this type of feature importance is stored in model.feature importances. So let's start with univariate feature selection. So one way to do that is to use Pearson's correlation coefficient. So calculate correlation between our feature values and target values for each single feature. And then we will select the features that have high positive or negative correlation. So we want something close to either +1 or -1. And here we can see the correlation coefficients for all these features. So the linear feature with low noise has highest correlation, followed by nonlinear feature with low noise, and the linear feature with high noise has even lower correlation. So you see that the correlation coefficient is decreased by both nonlinearity and noise. And here, a highly nonlinear feature has close to zero correlation, and the unrelated feature that is made only of noise has zero correlation, as we would expect. So how can we select in scikit-learn features based on correlation coefficient? So scikit-learn doesn't directly calculate correlation coefficient, but it has a scoring function f regression here that calculates f value. Now, f value is directly related to correlation coefficient, but it's a value that we calculate when we perform a hypothesis test that coefficient of linear regression is different from 0. So now that we have our scoring function that we know is related to correlation, we can build our feature selector, and this time we will use select k best. This feature selector simply selects the predefined number of best features. So in this case, we have scoring function f regression that will calculate f value, and we will select 3 features. So this selector is a transformer object, so we can transform the features using fit transform. And but we also need the target value this time. And if we then, after fitting, call function get support with indices equal true, it will give us the indices of the selected features. So we can see, as expected, that scikit-learn selected for us the first 3 features according to the correlation coefficient. The alternative way to measure feature importances is mutual information. So mutual information measures how much information is in common between the features and targets. So both of them are understood as a random variable, and we measure how much information they have in common. So obviously, we are looking for features with lots of information in common, which means high mutual information. And we can see from these values of mutual information for different features that importance is decreased primarily by noise, and is suitable for nonlinear and not unique relationships. So actually, in this case, highest feature is again the linear one, but it's closely followed by this highly nonlinear, non-unique feature. And that's because it has low noise. And only after that, rank third is this close to linear feature. Again, as we expect, unrelated feature has zero mutual information, and noisy feature has low mutual information in this case. So the code to select features using mutual information is very similar to correlation coefficient. We have scoring function mutual info regression, and we will put it in as a first argument of select k best, which is our feature selector. And we will again choose 3 features to select. And we see that we now selected features 1, 2, and 3. So you see that this is different. These highly nonlinear features got selected because it has low noise instead of the noisy linear feature. So far I showed you scoring functions for regression, but there are versions for a classification as well. There is a chi-square test. There is a f-value for classification and mutual information for classification as well. Let's now move to model-based feature selection. So we already said that if we have a linear model, we can use the coefficients or weights to select the features. And in this example, we choose lasso model because we already said that applying L1 norm penalty results in sparsity. So using lasso, we can reduce number of features more effectively. We will use lasso CV. That's a model in scikit-learn that implements lasso, but at the same time also tunes the hyperparameter lambda, so we don't have to do it ourselves. And this is the value that we obtained. And here you can see the resulting coefficients from the fitted model, lasso model. Here is the scikit-learn code. So this is our model, lasso CV. And we will use a selector that is called select from model. So this selector expects the model as a first argument, and we can also set a threshold on the coefficients in this case. So we will choose coefficients that are larger or equal to 0.01. And we can see that with this method, we selected feature 1 and feature 2, which are the two features that have a linear or close to linear relationship with targets and low noise. Now we will change the model and we'll look at random forest. So we already said that the random forest also returns feature importances, but these are based on decreases in impurity in a tree. And here you can see the importances that were calculated using a random forest. You see that again, linear feature had the highest importance, but this is followed by the highly nonlinear feature that was um, considered by random forest as the second important. Now, here is the code. It's very similar to when we use lasso. So our model now is random forest regressor. Our selector is select from model. So we'll put a random forest regressor in the first argument and threshold again in the second argument. And we see that this time we selected features 1, 2, and 3. So the highly nonlinear feature was included. This is because random forest regressor is able to model nonlinear relationships, unlike lasso. Okay, so we have the last feature selection method left, which is recursive feature elimination. So this method is also model-based, but there is a different algorithm how the features are selected based on model. This method recursively eliminates the least important features. So this is how the algorithm works. First, we need to select a ranking model that will rank our features. And in this example, I selected rich. And then we fit the ranking model to the whole set with all the features, and we eliminate the least important feature. Once we did that, we take the remaining features, fit the model again, and again eliminate the least important features. And this way, we will rank the features from least important to most important. So features of highest rank or rank 1 will be the ones that were eliminated at the very end, and the features with lowest rank, which will be towards the end of all the indexes, are the ones that were eliminated at the very beginning. So we can either select the predefined number of highest rank features, or we can use scikit-learn object RFECV, which stands for Recursive Feature Elimination Cross-Validation, which will also automatically select the number of features for us by calculating cross-validated performance of the model. So you see, if we define this RFECV selector with the model ridge, the selector will select these two features 1 and 2. So, of course, these are again close to linear features, and the reason for that is that we use ridge, that is a linear classifier, so it cannot deal with nonlinearities. So let's summarize our feature selection results. So we've seen that all methods selected features 1 and 2. These two features are linear or close to linear and have low noise, so they were always suitable. Feature 3 was interesting. It was selected by mutual information and random forest, and this feature was nonlinear and not unique, but had low noise. And we can observe that it was actually a very good feature in combination with feature 1, which is linear, because combination of these two features made the relationship unique. And also, if the model is able to model nonlinear relationships as random forest, then this is a highly predictive feature as well. But this feature was not suitable for linear models. And finally, feature 4 was always excluded. This feature was made entirely out of noise, so it was completely unrelated to target values, and this is what we expected. So let's look at our application of prediction of age at scan. And recall that the multivariate linear regression leads to overfitting. And what we want to see now is whether feature selection can prevent overfitting and result in a good performance. So here I compared several different approaches. So this is no feature selection where we keep all 86 features and it's overfitted, as you already know. Then there is the univariate feature selection using correlation coefficient, and here the best performance was achieved for 2 features, and you see that overfitting was greatly reduced. Then a model-based feature selection using lasso resulted in best performance with 6 features, and this resulted even in better performance. So we have 1.18 weeks cross-validated root mean square error. And recursive feature elimination, where the ranking model was linear regression, performed best with 4 features, and we had cross-validated root mean square error 1.21 weeks. So what we can conclude from this result is that feature selection can prevent overfitting in multivariate linear regression and lead to good performance. Actually, the best performance that we achieved was similar to ridge regression, which was the best regularization method that we've seen in the regression lecture. And also that model-based feature selection and recursive feature elimination perform better than univariate feature selection. And the reason for this is that these methods can also look at interaction between features, not just their individual importances. So one last thing I want to discuss is interpretation of feature importances. So feature importances give us information about most predictive features. And if we interpret the machine learning models that we managed to train for our biomedical applications, we can gain new insights into these applications, which features actually matter for prediction, for example. But can these feature importances be directly used to draw conclusions? So unfortunately, there is a problem with this. And the problem is that we can have correlated features in our data set. So many methods will select only one representative feature for all correlated features. And that way, some strongly predictive features will get lower importances, which of course doesn't really correspond to their true value. So this is obviously a problem for interpretation. And I want to demonstrate it on our example from previous slide. For the 3 feature selection methods that I evaluated, I here selected 3 top ranking features. And you can see that they are actually different for each method. So this demonstrates the problem. I will also demonstrate this problem using simulated example. So we will have 3 highly correlated noisy features. They are all linear features and they have the same correlation with the target values. And this is the original model from which they were generated. So the prediction should be just average of these 3 features. But if we apply various model-based feature selection methods, you see that we will get different importances. So we can see that ridge regression is most stable. So we get similar importances for our features. This is what we would expect. But lasso regression will have unequal and random forest will have unequal feature importances. So that tells us that these 2 methods tend to select one feature that represents the whole cluster of correlated features rather than ranking them equally. Now, this instability unfortunately prevents interpretation of the importances of individual features. This is not a problem if our goal is only dimensionality reduction, but if we want to gain insights into our application, then it is a problem, unfortunately. So there are some advanced solutions to this problem. One of them is stability selection. In this case, we will run feature selection method on different subsets of samples and then calculate statistics on how often are these features selected. This way, every time we have different subset of samples, the noise will become different. So idea is that over time, if you have sufficient number of different subsamples, this noise should average out and we should arrive to true importances of these features. Second type of solution is feature merging. So we can identify pairs or even clusters of highly correlated features, and then we merge them. Either we drop the less predictive ones and choose one representative features, or we merge them, for example, averaging or PCA. So this is all I wanted to tell you about feature selection. There is a tutorial in form of a Jupyter notebook, and there is also solution available on Kits. And one last thing that you need to do today is the quiz, feature selection. And after this quiz, this is the end of the lecture.